Okay, now we are, my baby was crying, so I had to help her take her nap. Where were we? Right, so we were doing mass, and this is the mass at rest, not the relativistic version. We did spin, and then we're looking at effective charge. Originally, in the first paper, I just looked at the charge for the stationary case, but the light charge hypothesis actually makes a pretty different prediction, which is that not only do you get length contraction relativistically, but the charge contracts relativistically as well. So you end up, if you look at the relativistic case, it ends up being right here that the effective charge ends up being the elementary charge divided by the square root of the fine structure constant times the Lorentz factor to the 1/4 power, or I guess to the half power, or whatever, because it's already to the half. So anyway, so yeah, and then this, I'm not going to go over this too much. This is kind of in the papers anyway. So then if we look at the relativistic mass as the radius contracts, you get this interesting kind of simple explanation for how you can blend a quantum picture and a relativistic picture. So if you just look at how the mass was originally defined for the stationary case, you get mass equals h over some constant times the radius. And then when you look at it relativistically, when you take like 1 divided by the Lorentz factor, you see that the Lorentz factor gets tied to the radius. So you see that that factor of 1 over the Lorentz factor is the same as the length contraction of the radius. So you get length is just the base radius times the length contraction, and then the mass is just the mass divided by the Lorentz factor. So this kind of gives like a really simple explanation for it. Because the electron is not a point particle, it just the radius contracts, and then that affects it relativistically in terms of the mass and the radius in a really simple way. The other thing I would like to point out is that I think the perspective in mainstream physics is that the more energy you hit an electron with, the smaller the effective radius gets, which is supposed to be proof that it's a point particle. But if you consider it with in a special relativistic lens, it's like, well, yes, the effective radius becomes smaller and smaller because you're hitting it with more and more energy, and the radius is contracting. So they take that as proof that it can't have a radius. I take that as proof that it has a relativistically contracting radius, but, you know, to each their own. Anyway, let's go to page 3. Or that was page 3, page 4, I mean. Anyway. So now we're gonna go, come on. We're gonna go to the magnetic moment derivation. Because in this model, the electron is something that has a structure, we can just look at it structurally to determine the magnetic moment. So typically for a current conductive wire in a loop, we just look at the magnetic moment of that wired loop as the current times the area of the loop. And here we just say that, you know, the current is the change in the charge over the delta time. In this case, the delta time is just, you know, one cycle, and the charge is, you know, the effective charge is previously determined. So when you just put that together and you get the area, you get this expression, which if you substitute out the radius at rest, you get this expression, which when you sub that in, gives you the Bohr magneton value. So you just swap that out, and then all of a sudden you get this expression, which would imply that the g over 2 value for the anomalous magnetic moment is actually just 1 over the square root of the fine structure constant times 1 minus v squared over c squared to the 3/4 power. I'm not going to go over this too much. It's in the paper. But there you go. There is a, you know, you don't have to sum up to infinity and subtract infinity and all that stuff. You can just get the value in like 5 lines. Well, it's not 5 lines, but less than 10 lines of basic algebra. So I feel like that alone makes it worth looking at. I mean, to be fair, it doesn't predict this value to, what is it, like 12 sig figs? It only predicts it to 9, but that's because the C is in here, and the C is only known to 9 sig figs, so that kind of limits the number of sig figs you can get out of the final expression. But I mean, potentially you could always just figure out C to more sig figs, and then, you know, this would serve as something of a prediction. that could be experimentally verified or refuted based on the upcoming sig figs that you could find for C with more precise measurements. Anyway, so let's go on to the analysis of an electron in motion. I've been kind of stuck on this one for a while because I had this model for a photon and a model for an electron at rest, but it was like, well, what do you do next? What does an electron in motion look like? So here we have a photon, as I was showing you before, with the u spatial dimension, which goes up to the Planck length, and then an x, and it goes in a clockwise circle or whatever as it propagates forward at the speed of c. And then alternatively, you have the electron at rest here, which is basically kind of wobbles about the u-axis at the Planck length, at the order of the Planck length, and then it goes in a circle at like, I think it's like 3.86 times 10 to the negative 13 meters, and you might be thinking, no, that can't be because electrons are known to be smaller than that, but I am putting my foot down and I'm saying this is the radius of an electron at rest. Everything else you see is an electron that has relativistic length contraction happening that you're seeing. So I'm saying that this is what an electron at rest looks like, and when you see it have a smaller radius than that, that's because it's undergone length contraction. Yeah, okay, next page. Alright, so then I go on to look at the electron again, and I say, okay, looking at it a different way, if we look at it in the z direction with the y direction, we have the positive charge and the negative charge, and they're going towards each other kind of at c, so they end up going in a circle at speed of c. This is for an electron at rest, and it has the largest radius, but its propagation in the z direction is 0, so this is a line. Z over time is 0. It's not moving, it's stationary. And then we have what I think will be an electron in motion. So we have y and we have c, we have y and z, and then if we look at the c vector, it's no longer going towards the other one in the y direction. It has both a y and a z component. So basically the y component will make smaller and smaller circles, which is your length contraction, but the z component will become larger and larger and will increase its speed. And then this becomes pretty simple, right? Like distance in z divided by time in t gives you your net electron speed. And then this becomes interesting because you can be like, oh, okay, now it makes sense. Like when this speed all of a sudden becomes c, then you can no longer have something with mass anymore, or at least for an electron, because it has no component to finish the circle, which is no component to finish the cycle, which means you can't have that EV divided by c squared anymore. So it's no longer something that contains mass, it's more or less like a photon at that point. And you notice that the radius contracts. So I suspect there's this, I'm calling it the transition point at this point. From here on out, the rest of the presentation is more just exploring ideas, and they become increasingly less grounded, so it shows more of my direction of exploration. I'm not saying any of this is grounded at this point. It's I'm trying to work on this in simulations. I'm getting something pretty close, but it's still a work in progress. If it does work, then I'll be at a good spot to put out another paper for the electron in motion. As soon as that's working, I can finally do the Compton scattering with an electron and a photon hitting each other and bouncing off. That'll probably be a different paper if I get that working, just because the simulations are very slow, like very slow. So yeah, let's go to the next page, page 6. So then I'm calling it the transition point. Basically I assume this is all assumptions, and then I make some back of the napkin calculations off of it, and then I spiral off into sheer speculation. So none of this from the rest of this video is grounded, and I'm not pretending it is. I'm just putting it out there as like what I'm investigating right now. So basically, as the radius contracts, I assume that the maximum it can contract to is the Planck length, because the photon's radius is the Planck length, or twice